So I work at DeepMind, which is an institution, a research institute, which is run as a private company, which is specifically dedicated to working on trying to find out how to build general-purpose artificial intelligence that can learn in many conditions. And it was founded in 2010 by Demis Hassabis, Mustafa Suleyman, and Shane Legg. And in order to be able to scale up all that research, which is computationally demanding, the acquisition in 2014 by Google was very welcome. Now, DeepMind operates on an independent, semi-independent basis from Google, and it's under Alphabet. And we are based in London, as well as in, with smaller offices in Montreal, Edmonton, Paris, and Mountain View, close to Google. When I started 5 years ago, there were 100 of us. Now it's 1,000 people. So I don't know everybody by name anymore, but we come from many different countries. And actually, I conducted this a few months ago, this extremely unscientific poll, just how many nationalities are there at DeepMind, and that's the answer I got, lots of flags. We are in the business of doing research and publishing it. So the kind of research that is interesting for DeepMind, as you might guess, based on the name, it involves a lot of deep learning, as well as the original motivation for deep learning, which is computer vision, which is to exploit regularities in the data. This is done in a Bayesian framework to model uncertainty, where you also look at the theoretical foundations of machine learning to basically make sure that it all converges and has some proof and guarantees. We look a lot at reinforcement learning, learning from delayed gratification with applications to control and robotics. We get a lot of dialogue and discussion with the neuroscience team, which gives us inspiration and priors that we can try to build. And we also do application of our research to science. Currently, I'm working on weather forecasting with the Met Office. And there has also been some work on protein folding and some work in optical coherence tomography. Finally, as we take inspiration from neuroscience, we also look even at higher level cognitive tasks that we may observe in humans. We look at natural language processing, which of course is quite remote from the capabilities of AI at this moment, and learning to learn, meta-learning. And this all has to be done in a way that ensures the deployment of AI is safe. So we actually work in collaboration with such people as Neil Bostrom, who published the book on superintelligence and paths and dangers to AI. And we really consider what could possibly go wrong. And in addition to what could possibly go wrong in the future, we look at what can possibly go wrong in the present. And that's why we look at the ethical aspects of AI as well, with DeepMind Ethics and Society and several research scientists working in that field. As you may have seen in the press, DeepMind does a lot of work on learning to play games. Some examples of such games include the Atari games. So here is an example of Breakout, where the agent finds a strategy by self-play, or the game of Go, which more recently has been published, as well as chess, something that can be learned from scratch, tabula rasa, by an agent doing self-play against itself. And more recently, there has been some work in partially observed environment using the StarCraft 2 game platform, where the concept consisted in essentially trying to learn complex strategies, not knowing what the opponent is doing. I didn't do any of that. My research at DeepMind has been about navigation, learning to navigate, and we looked at both the partially observed environment game, as well as the neuroscience foundations, and we even applied it to real-world photographic images to try if this can scale up to more difficult environments. So I'm going to talk about deep reinforcement learning, which is essentially the bread and butter of all those algorithms that have been deployed to play games. In the deep reinforcement learning, we have a simulation, an environment, a game, a three-dimensional game, or something we built on top of Street View using photographic images. And that environment is where an agent is situated. That agent gets observations of the environment. So for instance, first-person view from the point of view of the agent in an environment that's much larger. And that agent can act upon the environment. In the case of the game of Go, it's moving the stones. In our case, it's basically moving around. And basically, the interaction is at the level of what the agent sees with the environment. In order to facilitate and to encourage the agent to actually do something, we use a reward structure. That reward structure is what defines the game that the agent will play. And the goal of the agent is simply to maximize its rewards. So you can imagine that choosing a reward structure has an impact of what the agent will learn. In order to also facilitate that learning, we encourage the agent to make predictions about what will happen next. It's very easy to think of examples of what predictions to make in the case of navigation. What is behind the wall? Navigation has been considered as, by the research committee at DeepMind, as one of the important tasks on the way to more general artificial intelligence, because it's probably one of the simplest games that, and problems that force an agent to have to display some level of autonomy in an environment. The agent, as it goes around, needs to be able to answer two questions. Where am I in that environment? And how do I get to where I want to go? Where am I going? In order to be able to plan a sequence of actions to get there. And that means that as the agent is moving around, it may have to answer questions such as, where did I start? Have I been there before when it comes back on its own footsteps? Loop closure in robotics. And finally, how distant is A to B in order to estimate the amount of energy that the agent may need to go from A to B? So I'm going to cover, in the rest of this talk, the various problems on which I've been focused. The first one is exploration. So just being able to actually go places in that environment. The second one involves memory. And memory enables the agent to exploit a policy that it has learned while exploring the environment. Representation is what comes naturally as a question when we interacted with neuroscientists who were interested in how the mammalian brain represents spatial location. And we try to actually interrogate the activations of a neural network to see if such representation also arises. As I mentioned earlier, we're going to work at the later stage with street view images, so real-world data, and look at problems of transfer, learning on some cities and transferring to different unseen cities, as we are normally capable of doing. And this can be done using different modalities or using language instructions. The first problem, exploration and memory. Well, before I dig into that, I need to actually say a few words about the algorithms themselves. So we are using convolutional neural networks, which have been extensively published in the 80s and 90s. The two founders of deep learning who really focused on that field are Professor Yann LeCun, who was my PhD advisor at NYU, and Professor Jeff Hinton at the University of Toronto. He's now at Facebook and Google. The convolutional neural networks, what they do is that they exploit, like the visual cortex, which we always use as an inspiration, they exploit the structure in the data. And they process the data layer by layer, just like the V1 cortex, V1, V2 layers of the visual cortex. And that means that information is processed in a local way with local connections, so you can formalize it as convolutions. And then the following layers are processing at this slightly coarsened up feature space, and so on, up to the last layer. And these are essentially mathematical operation, metric multiplications, and some nonlinearities. And here you can see what in '96, this beautiful visualization, a neural network was seeing as it was looking at images of digits and the first, second, third layer and the output of the classifier. The other algorithm that we use is recurrent neural networks, popularized by Professor Joshua Bengio and Professor Jürgen Schmidhuber, Montreal and ICLR in Switzerland. So those networks exploit the property that things do not, need to be memorized over time. So in this case, the neural network has an initial state which is propagated forward in time and updated with new observations, and a new prediction is made at time 0, and then again at time 1, new observations, and carry on the hidden state, make a new prediction, and so on and so on. And those predictions can be, for instance, actions in the case of reinforcement learning. And you can imagine that, and that's a problem of reinforcement learning, the reward often comes at the end. So you need to be able to propagate all that information back in time. So deep reinforcement learning, as I've been looking at it, is basically learning to play in a three-dimensional environment, in a three-dimensional game. This is that environment. It basically comes from a modified, sanitized version of Quake 3, open sourced. We call it a labyrinth. And in that environment, the agent, the neural network, is taking in observations, pixel images, which are fed to a convolutional neural network. And after that convolutional neural network is then fed to a recurrent neural network, there are actions and an estimate of a value function, which is basically how likely is the agent to get a reward in the future. These are the two predictions made by the neural network. And those predictions, so a value function prediction and the so-called policy of the actions, are used for the network to actually take actions and to sample actions from a probability distribution. The game is defined by the rewards. In this case, apples bring +1, and this floating thingy, which is kind of orange, reddish, gives 10 points. That's the goal. The agent maximizes reward by going to the goal. Yes, the agent will also make predictions about, for instance, the depth field. You use the Z buffer of a game to derive that information of depth. So in the first paper, that actually took us 2 years to publish because we started in 2015 we had to build an environment and then build the games and then explore all the possibilities and difficulties of the task. So in that paper, Learning to Navigate in Complex Environments, we have such an agent. And you will see this very first task is taken from neuroscience. It is an eye-shaped maze. So this is how it looks like. The agent spawns somewhere, and it tries to explore. It doesn't see a goal. No, nothing. Nope, 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 nope. Oh, sorry, goal. Then it respawns during the same episode at a slightly different location and a slightly different orientation, and it needs to remember where the goal was and to exploit, to come back to it. And the only way for the agent to derive information is through, well, the reward structure. And as you can see, as it gets close to the goal, the value function increases. So this is an example of a navigation in the maze, which is, the maze is static and the goal is always at the same location, but the agent can start anywhere in the maze. And we added this decoding task where the agent would predict where it is, learn to classify its own, using a classifier to predict its own position in the maze. So that's a different maze. And well, the video continues with other examples. We had some limitations to that game. Is that those limitations were the following. If we had a completely random environment, the agent would not be able to actually properly learn after one exploration where the goal is and remember it. In the case of a large environment. It worked with small iMaze, but not in the large environment. So we continued our work and published this other paper, Unsupervised Predictive Memory in a Goal-Directed Agent, which did exactly that, 5 minutes. So in that case, the agent is making a prediction of its value function, but also it uses a read-write memory to actually write its own position. And it's using it to derive information during the rest of the episode. And it manages to do so well in the exploit. Then we looked at the representation side. And in the case of representation, we have something already given by biology, the so-called place cells and grid cells. So place cells, discovered in the 70s in the hippocampus, are cells that fire indistinctively over the orientation of a rat, but for a given specific location. And in 2005, grid cells were discovered, which fire on a regular hexagonal grid, which is very weird and very surprising. And that firing pattern happens at different scales, and different offsets and orientations. The authors of those papers won the Nobel Prize in 2014. Here we can see an agent going, a rat, let's say, going around, and the firing activity of the grid cells. And this firing can happen in multiple scales. And the idea, the hypothesis, is that those grid cells are connected with place cells, and the grid cells can be used as sort of a decomposition of space to make a prediction about the place cell location of a rat. So we took that idea and implemented it using a recurrent neural network. And that recurrent neural network was fed with just the velocity, the egocentric velocity of a rat, and the initial starting position. And as the virtual rat, it was just an agent, was moving around, the rat, that agent had to predict its position, so predict place cell activation. And we observed that the representation inside the recurrent neural network, the LSTM, were corresponding to something we would observe in biology. So these are rate maps, activity over a two-dimensional space, observed in our agent. And you see that a single unit of the hidden neural network fires on something that looks like a grid. We did a different kind of analysis looking at spatial autocorrelograms, and here we noticed that it really fitted what was observed in biology. And some specific cells were responsive to, were acting as grid cells. Other cells were acting in a different way, like head direction cells. They were responsive to a specific orientation of the agent. Then we replaced this framework by including additional visual inputs and training an agent to actually navigate in a visual environment and using visual inputs to reset periodically the position of the agent. And we had exactly the same behavior. And so we integrate that, again, into a larger agent that was trained using reinforcement learning to go to a specific goal. And that kind of agent achieved a much better performance in navigating in complex environments and remembering where the goal was compared to the previous ones that we have built. More interestingly, that agent was capable of exhibiting a shortcut behavior. So in a task, for instance, it would start here and the goal would be there. All those doors would be closed, and the agent would have to go all around to get to the goal. Then, at the end of the episode, the doors will be open. The agent will go straight to the goal. More interestingly even, we noticed that that presentation actually defined a Euclidean space. So we could directly decode with a linear decoder the distance to the goal and the heading towards the goal. So that work was actually praised by the original Nobel Prize winners for that work because it could be seen as sort of an algorithmic confirmation of some hypotheses observed in biology. So I mentioned real-world data, and here I'm going to skim a little bit about this. Basically, we replaced all that 3D environments with Street View. So we have observations of 60-degree field of view images. And we forget about the map. That's not seen by the agent. Those observations come from panoramas. And we trained on actual locations in Street View in central London, Paris, and different places in New York. The agent would have 3 possible actions: move forward, if it's possible, otherwise if it's facing a sidewalk, it's a wasted action. So move forward, if it can, or turn by left or right by 10 degrees. And the task was starting randomly, giving a random destination to the agent specified as latitude, longitude. The agent had no idea what latitude, longitude was. It was just 2 numbers. And the agent would get only visual observations, RGB images, and those target destinations. The agent had to navigate without any map inputs and without knowing its current coordinates to the destination. So let's see what happens in the following video. Well, there's even music. I forgot about that. So this is an example of an agent navigating in Paris. A trained agent. It's after 1 billion frames of exposure to the environment. So the agent starts over there. That's the goal location. The agent only knows the lat long of a goal destination. It doesn't know its own position. And as you can see, its policy is pretty good. It goes pretty straight to the goal. Don't mind if you see that the agent is going against the traffic. We didn't use the direction of streets as any constraint. So it was just basically using a bidirectional graph, if you want. So that agent had a convolutional neural network and an LSTM to integrate spatial information for the destination, another LSTM for the policy, and we also investigated adding some additional compass predictions, and the agent did a good work. Essentially what happened is that the agent was able to memorize in various places an environment after playing a lot of games. In order to be able to achieve so, that agent had to actually, to facilitate the exploration problem, the agent had to be shown the goal initially quite close to its start position. Otherwise, it would never reach it. So we used a curriculum learning. That sounds familiar to teachers. So initially, the goal would be sampled within 500 meters away. And then as the agent would master that task, we would increase the distance to the goal. We looked at generalization, what would happen if we didn't sample goals during training time at some locations and then used those goals only at test time, and it did work. And then we looked at modular transfer between cities. So what would happen if we train an agent with some convolutional neural network to process visual information, and then the policy to make the predictions, and then a specific LSTM, a specific recurrent neural network for each city. And then the idea is that if you go to a new city, we just get rid of the location-specific LSTM, but keep the visual and policy parts and just learn a new one, do some kind of surgery. It's a nice way to not to forget, because basically we just keep the other ones in memory. So, and that did work, provided that the agent was trained on multiple cities. And that research actually inspired a continuation of that research about transferring to new cities using different modalities or language. So the problem is, as I mentioned earlier, that our agent memorizes an environment because the task is defined so. It has to learn an association between a goal destination and its current and the current visual observations. And so it's impossible for the agent to go to a new location and tabula rasa be able to navigate there, because it just doesn't know what it means, that new destination. What if we define a task in a different way, using language instructions, which are relative? So based on your current position, you need to go forward to the end of that street and then turn left, and so on and so on. We got them from Google Maps. And we trained the agent in bits of New York and Pittsburgh, and then tested in other bits without any retraining. And it did work to some extent, but it's still work in progress. And so here, basically, we had, keep going back. We had an extra recurrent neural network that was processing text instructions and converting them to a presentation that can be used by the agent. And yes, we also looked at another kind of transfer, which is using both aerial views, top-down, like when you look at a map before going to a new city. Sometimes you do that, right? Yes. And at the same time, the ground view. And so we would train an agent with using both views to navigate, and then adapt using only the aerial view in a new location. So the agent would navigate using only that map, and finally test or retrain using ground view. And that did work also to some extent, but it's still work in progress. OK, I think I'm running just out of time. So I need to acknowledge, well, a lot of people who have collaborated with me during all that time. And this is a list of papers. Thank you.